A titration is a process in which a solution of known concentration, which is the standard solution, is added to analyze another solution. The titrant, which is the solution of known concentration, which we usually put in the burette, we have equivalence point or stoichiometric point, and that's the point in which just enough titrant has been added to react with the substance being analyzed. At this point, we have moles equal to each other. So the moles in the flask of each substance reacting are equal. An indicator is a chemical which changes color at or near the equivalence point, and we're going to choose our indicator to change color at that point. We'll learn more about indicators later in the year. And then the end point is the point at which the indicator actually changes color. So equivalence point and end point should be very similar depending on which indicator you use. So in a burette, or in a titration, you're going to have a burette with a known concentration. You open it by turning this dial, and then the liquid starts pouring into your Erlenmeyer flask. While it's going in, you should be swirling the flask, and you can do it dropwise as it's getting closer and closer to the end point. You can tell because it's going to start changing color, and the longer it takes for the color to go away, the closer you're going to be. The molarity of an unknown solution can be then calculated from the molarity of the standard solution and the volume that we used. Remember that molarity is moles over liters. So if you do the molarity times the liters, that'll give you moles. But again, this is a stoichiometric equivalence, and so we also have to take into account what's reacting. So we either have to have a balanced equation, or if we use this equation for an acid-base titration, it takes that into account by relating our number of hydrogens and number of hydroxides, because those have to equal for it to neutralize. So IA is the number of hydrogen ions the acid produces. VA is the volume of the acid. Because this is a modified dilution equation, and because we have volume on both sides, volume can be in milliliters, it also could be in liters. And the molarity must be molarity, but that's of our acid. For IB, that's the number of hydroxide ions. VV is the volume of the base, and MB is the molarity of the base. Again, we don't need to use this equation. We also could write out a balanced equation and then just make sure that we have our mole-to-mole ratio in there. So on this one, we have a base reacting with an acid. So my IB is equal to 3 because notice there's 3 hydroxides. And my IA would equal 2 because there's 2 hydrogens that can come off. So I'm going to put all of my acid on one side. I have 21.6 milliliters of 0.5 acid. So 21.7 milliliters, 0.500 molarity of my acid, and I have 2 hydrogen ions. On the other side, I have 26.4 milliliters. I have 3 hydroxides, and I'm trying to find out what the molarity of the base is. So to solve this, I just need to divide by my 26.4 and my 3. We had 3 sig figs, and so we get 0.274 molarity. Go ahead and pause the video and try this one on your own. Restart when you're done. So on this one, our perchloric acid has an IA of 1, and our base is an IB of 1 because we have 1 H and 1 OH. So in this case, my molarity of the base should have been 0.218 molarity. If a pH meter is used to monitor an acid-base reaction, it's common for pH and volume of the titrant to be plotted on a graph, as shown here. The equivalence point is the middle of the vertical section. So this is my equivalence point. Equivalence point isn't always 7, it just happens to be in this problem. When we talk more about acid-base titration later in the year, we'll see that sometimes it's above 7 or below 7, depending on what's reacting. One important thing that we need to know is the volume needed to reach the equivalence point. And to find that, I just find the volume at the equivalence. So I follow that vertical line down, and in this case it was 25 mils. So the volume needed to reach the equivalence point was 25 milliliters. So based on that, it says if 30 mils of the acid was used, what was the molarity of the acid? Well, in this case, they didn't tell me what the acid was, but notice that I only have one equivalence point. Again, we'll see later in the year where maybe we have an equivalence point and then another equivalence point. So one equivalence point, 2, that means that there would be 2 hydrogens coming off. Or maybe it looks like a steep line, and then another steep line, and then another steep line, so that would be 3 equivalence points, so 3 hydrogens coming off. Really, the most you can have is 3 hydrogens coming off. But most of the time it's just going to be 1, like in this case. So my IA is a 1, and I can tell from this it's NaOH, and so my IB is a 1. So I've got 30 mils of my acid. I'm trying to find the molarity of my acid, and I know I only have one H. My base, if I look right here, it says that it was 0.1 molarity. And the volume was 25 mils. I want to use the volume to reach the equivalence. And again, I had 1 hydroxide. So solving that out, you get 0.083 molarity. Here it says, at 10 mils, does the container have more acid or base? Well, 10 milliliters, here's 10 milliliters. If I follow that up, notice the pH is less than 7. I'm also before the equivalence point. Any point before the equivalence point, I'm going to have more of the acid. So that means I have more acid. Then it says, well, where do I have NaOH as excess? Well, if my NaOH is excess, then that means I've already reacted all of the acid. So that means that it's got to be after the equivalence point. So any point after the equivalence, I'm going to have more NaOH than was needed. And that's why the pH starts rising rapidly, and why now I have a basic pH.